Thank you. So this is a bit of looking under the hood in my talk of last week in a particular and specific example. So let me give some, actually, is it better this way for people in the back? Do you see any difference between this and that? This is better, okay. Sorry? Diagonal. Okay, so what I'm going to discuss are the characteristic polynomial and its extremes for a class of random matrices called the CbetaE. But if you don't like random matrices, you really don't need to know too much about it. The setup is a particular joint distribution of eigenvalues. So think of eigenvalues on the unit circle in the complex plane. And suppose that you have a joint distribution which is proportional to the product of lambda I minus lambda j to a power beta. So this is a van der Monde type interaction or a logarithmic potential type interaction raised to the power beta. So if you to be in the same setup as the talks we heard earlier today, think of beta as an inverse temperature, and you have an interacting particle system, and you don't have to think about random matrices at all, at your own peril. We will see that it is useful sometimes to look at random matrices. One comment is that the case beta equal 2 is special. In that case, this model is just sampling uniformly a unitary matrix and looking at its eigenvalue. Okay, so that's all the input we will need from random matrix theory. And now I'm going to be interested in linear statistics. So by linear statistics, I mean just take the sum of f of lambda I for f a test function, subtract the mean, you get yourself a centered random variables. Could be real, could be complex. It depends on what you take as a function f. And the question is, what happens to that? This is a random variable. Note that I'm not normalizing by anything. And the question is, what happens when the dimension goes? And one of the surprises of random matrix theory is indeed, or of logarithmic interactions, is that indeed you do not need to normalize. So in particular, f is a function on the unit circle, so it's periodic. We can discuss its Fourier transform, let's call it f hat, and introduce a quantity sigma f square, which is the h1/2 norm of f hat. And it goes back to Sego that in fact you can compute such products, expectation of such products, and the answer. So the answer is given in terms of the Fourier coefficients, and in particular, ZF is, so you see the product of E to the F is just exponential of the sum of the F of lambda I. So this is just a Laplace transform of that variable ZF without the expectation. Now the expectation is going to be exactly f hat of 0 because lambda I is uniformly distributed under this law. Everything is rotation invariant. So if you move the n f hat of 0 to the left side, which amounts to subtracting the expectation, what you get is exactly a Gaussian variable. Maybe there's a factor of 2 floating around. I'm not sure. Okay. And this was actually taken up by Johansson in 97 and by tools coming from integration by parts and some properties of these measures. He gave a sharp rate of convergence for these expressions, and actually not only for beta equal 2. So the strong Shego result is for beta equal 2, but in fact, the result is coming in general. Okay, now we are going to be interested in the characteristic polynomial, and more importantly, to the log of the characteristic polynomial. So, of course, the log of the characteristic polynomial, you can rewrite as sum of log of z minus a eigenvalues, and therefore it corresponds to this function log of 1 minus x. The Fourier coefficients of this function are of order 1 over k. The case Fourier coefficient is of order k. So sigma f square, what I call sigma f square, is infinity. Okay, so the previous theorem in particular does not apply, and it does not apply in a strong way. So it's not just that the proof doesn't work. The proof was for f continuous and smooth, but in fact, the result cannot. So the answer will not have a finite value. So here I'm going to switch gear back to beta equal 2, to the unitary case. And the unitary case has the advantage that we can bring to bear some representation theory. And indeed, because there's a group behind everything, and we can talk about random elements of that group. And Diaconis and Shoshahani, using ideas of that type, we didn't write the year, but it was a while ago, I think the late 80s or mid-90s, no, late 80s, I believe, showed that if you look at the traces of this matrix, the trace of un to the power k's converges to a normal 0k, where this is a complex normal, okay? And in fact, what they proved is quite remarkable. They proved an identity, not asymptotic results, but in fact, they computed the J's moment of the trace, and they showed that the J's moment of the trace, also with a complex part, but I'm not writing it here, is the same as the expectation of the J's moment of a Gaussian of variance k, as long as the dimension is large enough. In particular, when n goes to infinity, these moments converge, so we have convergence of all moments, so we have convergence in distribution. Okay? And this is a remarkable, I wrote here converges. In fact, it's an equality. That's really what I meant to write. So really, you get here an equality for n larger. Okay, so if you have that, you can take our log determinant and now expand the log in power series. So when you expand the log in power series, you will get the trace to the power k times z to the power k. You will note that I did not write z minus u, but u minus z, my identity minus z un. That's of course the same up to a shift by z to the power n. And we will be mostly interested in absolute values, so that will not make any difference. And then you get this power series. Now, from the previous result, the trace of un to the power k converges to a Gaussian of variance k. So divided by k, it converges to a Gaussian of variance 1 over k. So what you got yourself is essentially a sum of ak z to the k divided by square root k, where ak are IID. I forgot to mention in the result, but the result actually is about mixed moments, not just moments, but mixed moments. The formula applies to mixed moments as long as the sum of the powers is smaller than n, and you get independence. So that was the result. So the mixed moments, they decompose into a product of moments, and each of the moments, we have that formula. So what you should expect is that xn of z behaves like the sum of ak z to the power k divided by square root k. This is a very nice object because now it's a Gaussian field. And not only it's a Gaussian field, you can compute the correlations of that Gaussian field, and lo and behold, this is a log correlated field in the sense that I discussed last time. So the covariances really decay logarithmically, or blow up logarithmically if you wish. By the way, the variance of this object, of course, here I wrote a sum from 1 to infinity, but it's not too hard to convince yourself that if you're in dimension n, of course, you shouldn't go to too high powers. In fact, there are only n independent powers. All the rest are given in terms of the beginning ones. And in fact, you can truncate this series essentially at n, which tells you that the variance is logarithmic. The variance at a point is logarithmic. So indeed, asymptotically in the limit, it blows up, which is consistent with the result of Johansson I stated before. Okay, so we have this. Why has it stopped? Okay, so we are at the point that we were before, namely that we have this power series, and the power series is truncated. The power series is truncated at n. Now, this was actually taken up and proved in a series of papers maybe 20 years ago. Keating and Fnace, Weyand, Hughes, Keating and O'Connell, all that at around the same period, and they indeed proved that the log determinant divided by square root log n converges to a Gaussian, and that you have a log correlated structure in the sense that either you take separate, basically in the sense that if you integrate this object against a test function, you get a Gaussian variable whose covariance is the one you would expect from formally having a covariance which is logarithmic. Okay, now, of course, we are going to be interested in extremes. And if for the case that was written here, so for this power series, we know the answer, because we have a general theory of extremes for log correlated Gaussian fields. And from that theory, you can read off the limit. And we know that in particular, mn star is a logarithmic term minus a log-log correction plus a random variable of order 1. And we even know that this random variable of order 1 has a particular shape. Okay, now at this point, I should warn you that you should be very careful with this analogy, because at the level of the power series, of course, everything is symmetric. The maximum and the minimum are the same distribution at the level of the Gaussian power series. On the other hand, at the level of the log determinant, the minimum is minus infinity, because the roots of the characteristic polynomials are on the unit circle. The eigenvalues are on the unit circle. So the roots are there. So the minimum value of the determinant is 0. So the minimum value of the absolute value of the determinant is 0. So the log determinant, the minimum value is minus infinity. Okay? So the analogy is good, but we have to be a little bit careful. And motivated by conjectured relations with Riemann zeta function, about 10 years ago, Fyodorov, Hayri, and Keating conjectured not only that this is a true picture, they did not come at it from this angle, but they essentially computed moments and from that conjectured the form of the limit distribution. But in fact, they even conjectured a very precise form of the limit. The limit is going to be a sum of two Gumbels. Okay, so the object that we talked about is just a sum of two independent. If you look at their paper, it's actually not conjectured in that way. They gave a formula for the limit distribution, but later Eliran Subag realized that that formula is really the convolution of two Gumbels. Very good. So that gave motivation to study this. And a few years ago, there was an attempt, the first attempt to deal with with that maximum, and there were a couple of papers that did that for the case of beta equal 2 with, I would say, a significant effort. And the results were essentially that leading order is indeed 1, the correction term is indeed 3/4, as it should be from the theory of low correlated gases. So you see that, excuse me, you see that there is some trace of the low correlation there. But both methods seem to be very hard to push further and also were limited to beta equal 2. And the big surprise, at least to these two teams, came very shortly after when Shaibi, Madul, and Najnudel, by using a completely different method that I will describe in a moment, proved not only that the two terms are as predicted before for beta equal 2, but actually that this random variable that you obtain at the end is tight. Okay? So what they proved is that for any beta, you have this kind of result. Okay. So okay. Yes, it stopped. I don't know. It stopped. Same problem. I'm not sure why I'm having this problem. I think I am connected. I'm not sure why it keeps getting disconnected. So, okay. So let me make a few amplifying remarks before I get to a more careful, a more detailed remarks on the method. There is a less developed theory also on the real line, so which would correspond in the random matrix world to the case of Hermitian matrices. And the theory on the real line for is most developed for beta equal 2, where you have tools such as Riemann-Hilbert methods that can allow you to do more explicit computations. In particular, there's a very interesting paper of Lambert, Paquet, and of Kleiss, Fass, Lambert, and Webb, and work of Krasovsky, Charlier, all the usual suspects in that kind of beta equal 2. For general beta, there is much less. There is work of Bourgade, Modi, and Payne, which uses a loop equation, and there's work of Fanny, Fanny Augery, Raphael Boutez, and myself, which does a CLT. The first one also gives multi-point kind of log correlated structure. And this seems to be a good base to go forward and analyze things, but it's much less developed than the circular case. Okay, there are also results. I've not discussed it at all Gaussian multiplicative chaoses, which are exponentials of the objects that you get in the limit. So exponential of these Gaussian fields viewed as a measure. There are results of that. I'm not going to discuss it today. Okay. So what was the very useful observation of Shaibi, Madul, and Najnudel? They used the theory of orthogonal polynomials on the unit circle, which I want to describe very quickly now. So suppose that I have a sequence of IID random variables that I call gamma j, which are of this distribution. So I wrote explicitly the distribution. It's not so important what exactly it is, except to note that the beta j grows like j, or like j times beta. Okay, and in fact, the variance of this variable will be 1 over beta j, so these variables will have variance 1 over j, roughly. And then complexify these random variables, namely take alpha j, which is the modulus of gamma times a random phase. Okay, so this gives me a collection of independent random variables. And now you can construct, there is a realization of matrices from the CbetaE in terms of certain 5 diagonal matrices. This goes back to work of Kilip and Nanciu, and you can look at the orthogonal polynomial associated with the spectral measure of that matrix. And if you do that, and the best source for looking exactly how is it done is the classical book of Barry Simon on orthogonal polynomials on the unit circle, which will give you more than you ever wanted to know on these objects. The point is that you have a recursion for these orthogonal polynomials. You have a 3-term recursion of this orthogonal polynomial in terms of these coefficients alpha k, which actually have a name. They're called the Verblunsky coefficient associated with the orthogonal polynomials. It's a very general theory, but the beauty is that for these invariant ensembles, you get very simple coefficients in terms of independent random variables. The emphasis here is on independent. So we have now mapped our original problem into a question involving a string of independent random variables, which true are not exactly Gaussian, but there are lots of them. So maybe some Gaussianity is going to be restored in the limit. So we have this equation, and I should say that this observation of Kilip and Nanciu came actually in reverse order from what I described here, namely first came an observation of Dmitry and Edelman in the Hermitian matrices case. They gave a 3-diagonal model for such matrices, and then Kilip and Nanciu found a way to push it in the unitary case. Okay, and the nice thing about this recursion is that you can write the determinant in terms of these orthogonal polynomials and one more independent variable. So if you give me the phi star, the solution of this recursion up to n minus 1 and an additional random variable, I can spit out the determinant. In particular, if I'm interested in the modulus of this determinant, if I know good information about the phi star and you give me this extra variable, I can transfer things from one to the other. Yes? This is not a distributional identity. This is an identity. So what do I mean by identity? Sorry? Yes, so, okay. So the reason there's a D is that because of the way that I wrote the recursions. In fact, you can write the determinant of a particular matrix, which is not exactly the one of Kilip and Nanciu, but involve replacing the coefficients. And it's not convenient to discuss it here because if you do that, you will lose increasing with dimension. So you will have to replace at each step all the coefficients. No, it's Kilip-Nanciu. This is Kilip, all this is Kilip-Nanciu, it's a representation. Actually, it goes back in the theory of orthogonal polynomials. It goes back to what they call the CMV representation. There's a whole story behind it that I don't want to get. Okay. Good. So in fact, there is a way, a more compact way to rewrite this representation in terms of what is called the proofer phases. So if you look at this recursion, it maybe doesn't look very much like it, but if you look at the recursions that I wrote here, and you try to write real and complex coefficients and use the fact that you are on the unit circle, then you can reorganize the recursion in an easier way. And in fact, here is a way to organize it. So if you write a recursion on phases, this is the object I call psi, then you can write that psi k plus 1 is psi k plus theta, the angle where you are on the unit circle, minus a quantity, which is log of 1 minus alpha k, the same alpha k's that we introduced earlier, times e to the I psi k, where this psi k are the previous step. Okay? So this is, of course, a Markov chain. If you give me psi, I can compute the next one. But the nice thing to note is that if you give me a particular theta, because the alpha is rotation invariant, it's multiplied by an exponential of a uniform variable on the unit circle, the distribution of alpha k e to the I psi k of theta does not depend on theta and does not depend on psi k of theta, because everything is an additive independent variable. So if I'm looking at a single theta, these psi's are actually a random walk, pure and simple. You just have a random walk, a scalar random walk, where you have an increment which is almost a Gaussian. Okay? And that's very good news, because it gives us a representation, at least at a single angle, that is almost for free. You don't need to do anything. It's just classical probability theory. Okay, those are not IID random variable, but because the variance decreases, but those are independent variable, and in particular, it falls very well into Lindbergh-Feller. So you get for free a CLT on this psi, and in fact, you can write the log of the phi, the orthogonal polynomials we care about, again as a random walk driven by these psi's. So again, the increments of the log are independent random variable. Okay? So for each fixed theta, we have a pointwise CLT. Of course, this is not jointly a random walk. If you look at two different thetas, it becomes rather complicated. And now I can state the result. So one thing that I want to emphasize is that for the determinant, because of this extra randomness we need to add at the end, we will need to handle at the same time the real and the imaginary part of the log determinant. And in fact, we will need to handle them jointly. Although in this presentation, I will kind of gloss over this. So the main result is what you would expect. So this is joint work with Elliott Paquette, which is now on archive. And it tells you that the maximum of the log determinant minus the right centering converges to a Gumbel plus an object. And this object we can identify. We have some limit representation of that object. We don't know yet that this is a Gumbel. This remains to be shown, but I think it's not very far. You have the same result for the imaginary part and also for the... And in fact, because of my remark on the determinant, it's very important to understand not just how does the maximum look like, but actually the relative shape of the real and imaginary parts near the maximal point. And the result, in fact, includes also that information, although I chose not to present it here because it's too complicated to state. Okay, let me say something about this variable W that was added before. So the variable W is the following. You look at something that is very close to a derivative martingale. So if that were a branching random walk, this would be a derivative martingale. And in fact, you have independent increments. So it's the exponential of this phi that we discussed earlier, multiplied by a linear term. So we saw such objects yesterday in Oren's talk. The only thing that makes it not a martingale is that we take only the positive part. But remember that we expect the phi k to be small compared to log k. There is a log k direction that makes it smaller than log k. Therefore, the quantity that is written there with high probability is positive anyway. So the plus or not plus shouldn't matter, and indeed for large k it does not matter, but it helps in the analysis. And one of the statements is that if you look at the total mass of that derivative martingale, or that object, the total mass converges to a limit, and our W is just the log of that total mass. Now that's very good news, because in the case of Gaussian fields, the ones with the series I discussed earlier, the total mass has been identified and is indeed related to the Gumbel, it's a log Gumbel. So we can have a hope. Of course, this is not exactly a Gaussian field, but it's very close. And so this part is at the moment conjectural, but one could hope to eventually close. Okay, so now I would like to tell you something about the proof. So how did CMN, who really had this decisive idea in this business of introducing this recursion, how did they do their work? So they recall that for a fixed theta, our phi k of theta is a random walk, and there is a natural time change here, because by n steps we expect log n variance. So there's a natural exponential change of scale, and so you expect it to behave like a Brownian motion with variance which is log k. And if you introduce the relative proofer phases, you get again a recursion of the same type, except that you have this extra theta when we look at different theta. Now, the mental picture you should have in mind is the following. If you look at this recursion, or let's look at this recursion for psi. So as long as there's a bit of a confusion in what follows, at the moment k is just a running index from 1 to n. Later k will be log of that. Don't worry about that. So if you look at this recursion, you can expect that when theta times k is much smaller than 1, two different psi's at two different thetas should be essentially the same. Because this term theta k is little, so the sum of thetas is little order of 1. Of course, it is pushed through the recursion, but still that's natural to expect. And on the other hand, when theta times k is larger than 1, what happens is that the variance of the noise, remember, the variance of the additive noise here is essentially 1 over k. So it's tiny. So if theta times k is of order 1, you oscillate like crazy, whereas you add only the tiny noise. So what you're doing, you're summing independent random variable with a different oscillatory phase. It's like summing independent random variables multiplied by a cosine of something that is rotating fast. And of course, this is going to be asymptotically independent of the value when the thing is not oscillating. Okay, so that's really what is happening here, and that's the mental picture you should have in mind. So the mental picture is that there is a certain k0. Now, I'm sorry, but I switched to notations in which k goes from 1 up to log n, because that's the triple picture I want to have. So as long as delta theta times e to the minus k, which was previous, is much smaller than 1, sorry, times e to the plus k, is smaller than 1, then the phi k of theta and phi k of theta plus delta theta is the same. And when delta theta times e to the minus k times e to the plus k is larger than 1, then the increments are essentially independent. So if you take the minimal scale, the minimal scale to worry about is 1 over the dimension. So if you take the minimal scale, it tells you that for any delta theta, there is a k0, which corresponds to where these two recursions split. And up to this point k0, they are more or less following the same evolution. And after that, they are completely independent. Of course, there is some fudge around k0, but that's the mental period you have to, the mental picture you have to have. And because of this exponential, it's well suited to this tree picture. Okay, good. So in fact, what we obtain from this mental picture is that phi k of theta is roughly a Brownian motion, and the two Brownian motions, phi k of theta and phi k of theta prime, go together up to the splitting point, and then they are independent. And of course, this is not true literally, it's not true pointwise, but if you accumulate things in blocks, then you have that. And in fact, that's a method that CMN are using. They do a coupling in blocks. They don't look at every single time instance. They look at times or blocks in which the increment invariant is of order 1. That block is decomposed to a lot of small pieces, so you get a Gaussianity for Friesen. And then they do a rather clever coupling by essentially freezing the coefficients during the length of a block. So if you freeze the coefficient, you get yourself essentially a Gaussian recursion. And that's how they can couple it to the Gaussian. Okay, so that's how they do it. Once you have this mental picture, you apply the methods from branching random walks, or the first moment, second moment that I described very quickly in the previous lecture. Okay, so now what will we have to do? Well, we have to keep track not just of the value of the maximum. There are several things that you have to do. First of all, because they deal only with tightness, in fact, you don't care about what happens in the beginning. It doesn't really matter. What happens in the first zillion excursions doesn't really matter. And because of that, they essentially throw it away so that you get into the Gaussian regime from the beginning. Okay? We cannot do that because we want an exact limit result. So that's one aspect. The other aspect is, remember, at the end, we really need to keep track of the function around the maximum, both the real part and the imaginary part, because we have to take a combination of them and kind of maximize it locally. So because of that, we have to keep track of a certain decoration, and the decoration is just what happened. We divide the interval 0 to pi to small intervals, which are, maybe I should draw it here. We are dividing this interval into small intervals, which are roughly 2k1 over n. And we are going to, if we keep our mental picture of the tree, this corresponds to a certain splitting point higher up here. And we are going to keep track of the whole configuration, the whole function in that region. So we look at the function, the value of the function somewhere here, and we add to it this kind of decoration process. And then we can look at, at the maximum over this small interval of whatever quantity we want. In this case, it's psi n. And then we can take a process which keeps track both of where we are, these theta j's, which are the points at this level, the decoration, and the value at that point. And the first step of the proof is to say the following. If we look now at the increments at the bottom of the tree, the variances are very small, so we can get a very good approximation in terms of a fixed stochastic differential equation that does not depend on n. Okay? So what we are going to have here is some kind of stochastic differential equation related to the evolution of the Brownian motions here, awfully complicated. We don't know exactly what it is. We can write it down, but it's rather complicated. And that stochastic differential equation gives us a law for the increment as a function of theta. So what we get ourselves is a path, a law on path. So this law on path, we call it pk1. It depends on k1. The length of the interval depends on k1. The length of the recursion depends on k1. So we got ourselves an object like that. And then what we can also do is look at the value at this point. But remember, at this point, the values are more or less constant for all the points in this interval. So we might as well choose one point here. In reality, I'm cheating a little bit. We'll do it slightly higher. But disregard that. So we have the value here. And then we have this decoration added to the value here. And the point is that these decorations, you can construct them such that far away points are independent. This is related to the fact that we are rotating very rapidly with speed related to theta. So if I take 2 points that are relatively far away, these guys are not independent. But if I take 2 points that are relatively far away, you can construct, you can couple all the Brownian motions involved in such a way that the increment here and the increment here are going to be essentially independent. Okay? And in fact, the increment here and all these increments. So this you can do. And in fact, you can construct a sum, an extremal process. I don't want to, it's not so important, the details are not so important, but you can construct an extremal process that keeps track of what is going on here and of this decoration business down here. And the claim I want to make is that if I condition on everything that happens up to here, the process I'll get in that situation will be Poisson. The reason is that, in fact, there will be typically very few points here which are high, and it is going to be very hard to pick up an extra height here. So the probability that this subtree brings it to my target, which is to be next to the maximum, is small. And therefore, it's unlikely there will be too many of them. And those that will succeed will be far away. But those that are far away are essentially independent. So an application of what is called the two-moment suffice in the theory of Chen-Stein Poisson approximation, so the Stein method for the Poisson approximation, give you that what you obtain is a certain Poisson point process, which is then modulated by what happened before. And what happened before, again, if I cut it at some level K2 and some level K1 here, when K2 and K1 are large, if I condition on what is happening here, okay, so first I condition on what is happening here, get rid of the decoration and replace it by a Poisson point process. Then I condition on what happens here. I have a similar situation. There is not much dependence between far away points. And to get high there will be not too many points that are close and that are high, so close together and high. So at the end, you can replace your whole picture by a Poisson point process with this K1 decoration. So really the main theorem, maybe I should say it like that, is that if you look at the extremal process and you replace everything by a Poisson point process whose intensity is related to this function dk2. So remember, dk2 was a certain derivative martingale that I introduced in the beginning. It was a function of theta. So if you introduce a Poisson point process which has intensity related to dk2 times the intensity of this guy, that is what you're going to see at the end. You're going to see just a Poisson point process which depends on K1 and K2. And as K1 and K2 go to infinity, the convergence to the Poisson point process is getting better. So the exact statement is that you can replace our original process extremal n by a certain Poisson point process that as a parameter takes as input this dk2, this random object at level k2, okay? Which we know converges almost surely. That was a proposition I showed you before. So we converge to a random Poisson point process. The only difficulty is that in order to make this convergence, I had to take this K1 larger and larger. So the process here is on larger and larger intervals. And in fact, what I care about is what happens near the maximum over this longer and longer interval. Okay? So we don't have a good description of, at the moment, of how it looks there. But in fact, it doesn't matter because it will affect the final result only as a constant shift. So there is an extra constant that will come from that into the limit law. Yeah, so this is more or less, yeah, okay. So just to kind of reiterate, once we condition on f of n of k1, we can construct the decorations and we construct them in an independent manner. And then for each ray, for each path leading to here, we do a variance reduction by only caring about paths that do the right thing. They don't go over a barrier, they stay in a good region, etc. And once we have that, we have the Poisson point process, this Stein method that I was talking about. And then we can condition on what happens at K2 and get everything encoded into this derivative mapping. Okay, so that's kind of the picture that I was trying to make. So what you'll get at the end is this kind of paths that are wider and wider in absolute term, in rescale term, but of course everything is multiplied by 1 over n. So in reality, they look at a very tiny part of the angle, but when you rescale it, you get a limiting process and you're looking near the maximum of this limiting process. You have essentially order 1 of those, and that describes the maximum. Okay, I think I will stop here. Thank you for your